All right. So let's begin. So today we will wrap up our study of MSTs, and then we will do a few more examples of maybe just a couple of examples taken from the book about how to go about solving greedy algorithm problems. And then in the second half of the class, we will start our next unit on dynamic programming. We will actually get back to some more examples of greedy algorithms when we do shortest paths, but we are changing the order in which we are doing things. So we will first go on to dynamic programming, and then we'll get back to more greedy algorithms. Okay, so recall key things about MSTs. So minimum spanning trees are trees that span the entire graph. So they cover the entire, they connect all the vertices of the given connected graph, and they do it in a way that minimizes the total, okay, the total weight of the tree. And key things to remember that we've gone over is cut property, cycle property. So cut property is if T is an MST, okay, and S complement is a cut to G. Then T should contain a minimum weight edge crossing the cut. And again, when I say a minimum weight edge, what I mean is the edge that has the least weight, but there could be multiple minimum weight edge. That's why I'm writing it as a minimum weight edge. Cycle property, T is an MST, C is a cycle, T should not, and I've noticed that I'm maybe writing it a little differently, but they're all than what I've written before, but you should see that they are saying the same thing. So T is an MST, C is a cycle in G, T does not contain okay. It's often very easy to think about a situation when all the weights are distinct, okay, and often you can make that assumption without too much problem. So if you think of all weights being distinct, then this statement becomes T contains the minimum weight edge crossing the cut, and this statement becomes T does not contain the maximum weight edge of the cycle. Okay? All right. So these are the two important properties to keep in mind whenever we are reasoning about minimum spanning trees. The other things that you should always keep this in mind, that if you have a tree, you add an edge, what happens? You get a cycle. If you have a tree, you remove an edge, you basically cut the tree into two parts. Into two and one part could be S, the other part could be a complement. And it's sometimes useful to look at this cut in G, okay, if you want to invoke the cut property. Okay? All right. So whenever you're given something to reason about minimum spanning trees, essentially the idea is that you can try out when you have to invoke the cut property, cycle property, add an edge to the tree, remove an edge from the tree, and things like that. That's basically the kind of arguments you would try to make. All of these arguments about adding edges and removing edges are kind of exchange arguments we are making repeatedly for many problems with greedy algorithms. Okay? Where if you are asked to prove that the minimum spanning tree has a certain structure, then you say, all right, if you give me a minimum spanning tree that does not have the structure, I will try to enforce the structure by adding and deleting something. Okay? Okay. So let me ask, before this going on and talking about the one aspect that was left before was Kruskal's algorithm. How do we make sure that Kruskal's algorithm runs in log n time? We will cover that. But before that, let me pose a few questions. Let's say I ask you to prove T is an MST. So T is a minimum spanning tree. S complement is the cut in G. Let UV be an edge of T such that U is in S and V is in S complement. Okay? True or false? UV is minimum weight edge crossing the cut. Is the question clear? Okay. So you have to try to, you might have a statement like this, and you have to try to visualize what is going on and reason about it. So the claim is, I give you a minimum spanning tree, and I give you a cut in the graph, the minimum spanning tree of G. So T is the minimum spanning tree of G. So G is the graph given to you. T is the minimum spanning tree given to you of that graph. S complement is a cut given to you, and I show you an edge in the tree that crosses this cut. Okay? Question: does this have the minimum weight edge? Is this edge the minimum weight edge crossing the cut? Okay, I would like you to all spend a couple of minutes working with a couple of examples, if this helps, and either proving the statement is correct or showing that it's false. How do you prove the statement is correct? Well, you can prove the statement is correct, for example, by trying to prove contradiction. So if it was not the minimum weight edge, then you can make an improvement in the graph by removing it, so in the tree, by removing it, adding something, using anything that you want. If it's false, how do you prove it's false? You give an example where everything that is stated above is true, but this statement is not. Okay, any questions about the problem? Anything that's that's not clear in the statement?
Could you repeat how do we do to prove it's false?
If you were to prove it's false, then so a statement like this, what is it saying? It's stating some conditions imply something else. So to argue that you are disproving P implies Q, the way to do it is to set the stage so that P is true, but Q is not true. So the way you set the stage that P is true is you give a graph, you give a tree, you give a cut, you give an edge in the tree, and that's crossing the cut. So everything has been set up. Then you say that, oh, it's not the minimum weight edge crossing the cut. Okay? So let me actually be more precise here. UV is the minimum weight edge crossing the cut in G. Okay? There are lots of edges crossing the cut in G, and UV of course is in G, right? Because it's part of the tree, so it's part of the graph. Is it the minimum weight edge crossing the cut in G? Alright? People have any? How many people think the statement is true? People think the statement is false. We are pretty relatively split. Good. Okay. So somebody wants to give a proof sketch of this. All of people said that it's true. Somebody wants to give a proof sketch? Yes.
So let us assume that it's not the minimum weight edge.
Okay. So this edge, let's call this edge E, and let's suppose it is not the minimum weight edge.
So there must be a prime which is the minimum weight edge.
Okay.
S.
Okay. So let me draw a picture S as complement. This is an edge E. That is E is the same as UV. Okay. It's part of the tree. So let me draw it like this. It's part of the tree. It is not the minimum weight edge. There is some other edge E prime that is crossing the cut. Whose weight is less than weight of E. Good. Okay.
So if this was true, then E prime would have been in the T, would be in T by the problem.
Okay. But maybe E prime is in T.
But then it would form a cycle.
Okay. So let's try to understand that. Good. So let's do systematically. So E is an edge that is in the tree. E prime is a minimum weight edge of G. Okay? So we are trying to derive a contradiction, and the contradiction we are trying to derive is, so what do we want to say about E prime? So weight of E prime is strictly less than weight of E. Okay? So then the claim is that this should not be possible, because otherwise E prime should be in T. But we haven't yet shown that E prime is not in T. So let's try to do that. can E prime be in T? Okay, so one suggestion was if E prime and E were both in T, this will form a cycle. Is that true?
No.
Not necessary. Okay, and you can imagine, if we draw a picture like this, this is a cut. There are two edges in the tree crossing the cut, and you have to have both of those edges. So E prime can certainly be in T. Okay, so now what? So maybe E prime is also in T. So this can the situation arise? We've just shown that it can arise. So in fact, that's a counterexample. Okay? If your graph was simply this, this is your graph. Okay? Look at this cut. What is the minimum spanning tree of this graph? The entire graph itself, because there are no cycles here, so you'll have to include. So both of these are. This is an edge crossing the cut. What is the cut that I picked? So, what is the counterexample? G is that graph, P is the same graph, S is U on one side, S complement VW on the other side. Is UV the minimum weight edge crossing the cut? No. Okay. So notice that it seems very similar to the cut property, but it's not. The important thing to understand is this is saying that T contains a minimum weight edge crossing the cut. That statement is saying that any edge crossing the cut is better be a minimum weight edge. That statement is not true and almost but a simple example. Okay. It also illustrates to you just you can across a cut you can have many edges from. Okay. Okay. Let me now that we have drawn this, let me ask you some other question. So this is more of a understanding of cuts. Is there a cut such that T has no edge crossing the cut? Is there any cut such that T has no edge crossing the cut? Can there be a cut? And a cut is not, what is a cut? Cut is some vertices on one side, the remaining on the other side. Can there be a cut such that T has no edges crossing the cut?
G.
No? Because if T had no edges crossing the cut, then T would not be connecting things from here to here. This is, by the way, nothing to do with minimum spanning tree. All it has got to do with is spanning tree. If a spanning tree has to cover everybody, it has to have edges crossing the cut. Okay? Is there a cut such that T has exactly one edge crossing the cut?
Yes.
How do you find such a cut?
The leaf on one side, one of the leaves on one side.
Okay. Whenever if you have a leaf vertex, every tree has to have a leaf. If you make the leaf on one side and everybody else on the other side, that will have exactly. Can you think of some other cut not involving leaves?
Just two nodes.
No, correct.
Which two nodes?
Any of the two nodes.
No, but let's say it's a big graph, big tree.
This is the only edge between, if you say two components.
Correct. So pick any edge of the graph, of the tree. If I remove that edge, that splits the tree into two parts. How many edges are crossing the cut in the tree? Exactly one. That's the edge. Okay? Which is why there is this misconception sometimes that, oh, there cannot be two edges. But basically what's happening is if I give you a tree, this is your tree, you pick an edge and you look at that cut. That has exactly one edge crossing the cut, by definition, because you found the edge and you removed it, it's split into two parts. Okay? That's why sometimes this picture is misleading. Okay, but okay. Let's try one more question. Can we move on? Okay, so suppose all weights are distinct. Okay, suppose all weights are distinct. Let's say G is the given graph. T is MST. U is any edge, any vertex of G, and let's say UV is the minimum weight edge for U. Okay. Is minimum weight edge for U in G. True or false? UV is in T. Okay. Again, is the statement clear? I give you a graph, any graph, it has weights and edges like it. I give you also a minimum span. T is any minimum spanning tree of G. U is any vertex of G, and UV, this edge, is the minimum weight edge for U in G. Okay? Prove or disprove that this edge better be in the MST. Okay, any questions about the problem? Okay, I'll let you guys think about it again for 5 minutes.
Yeah.
Okay. All right. How many people heard true? How many people think this is false? So let's try a false proof first. Yeah.
So if there's a cycle, here always said is that the weight between the edge between U and V is the minimum weight edge. But if there's a cycle such that there is a separate path from U to V and that has lower weight, then we don't pick the edge between U to V.
Okay. So let's try to understand this. So UV. So UV is the minimum weight edge for U. Okay, it has low weight. And let's look at the cycle property. So let's say this has weight alpha. And we look at the cycle property. And maybe there is a cycle containing UV. In the graph, right? Of course, the cycle does not exist in the tree. And so, one argument is, oh, this, by the cycle property, the largest weight edge cannot be in the minimum spanning tree. So it's conceivable that every vertex, every edge in this path is of weight, which is smaller than this, and alpha would be then the maximum weight edge. Okay? It seems like a compelling argument, but it's very important that, again, if you're trying to prove it, you would actually prove it by arguing that if UV does not belong to the tree, then you can actually improve the solution. Okay? If you're disproving it, what do? You give an example where all the statements that are listed are true, but the final. Okay? So while this is intuitively seems possible, really to justify it, you already give an example. So let's try to give an example. What does the example require? U has to have an edge to V of weight, some weight. Let's take weight 1 or 2 if you want. And you want to find a path from V to U in which every edge has weight less than 2. Okay? Of course, I think it's possible to come up with things. So, okay, but notice that all the weights are distinct, so I can of course make up numbers in between 1.5, 1.3, 1.2, 1.7. You agree that all the weights are less than 2? But what did I do?
You violate
It's not
one
as
of
I violated the property that this is the minimum weight edge. Okay, so you could have if you have a path in which every edge has weight less than this, then this edge will also have weight less than this. And this has to be another edge. So notice that this plausible intuition, when you actually try to formalize it as a counterexample, fits. Okay? Yes?
I have a question. So when we say that UV is the minimum cut edge for U and G, is
Minimum weight edge.
it's a, oh, this is weight. Or is
Yeah,
it-
WT.
Oh, weight.
Minimum weight edge. Yes.
So then, yeah, we violate that property.
Yes. Okay. All right. Any other comments? So let's try to the other side. So we want to prove it's true. Okay. How do you prove that it's true? Okay. Basically, the standard way to do it, and as I said again and again, is some kind of an exchange argument. You suppose all the conditions are true, but suppose UV does not belong. Suppose UV does not belong to it. Okay? And UV is what? UV is the minimum weight edge. Notice that all the weights are distinct. So there is exactly one minimum weight edge adjacent to U. Okay? It's not necessarily the minimum weight edge of the whole graph. All we know is it's the minimum weight edge among all edges that are connected to you. Okay, so what do? I give you this sum tree. And the graph is more complex. This is U. It does not include your edge that you really wanted to include. Okay? Sorry, there should be another way to reach. Okay, so what do we do now? So you add it to T. Basically, again, what do you want to do? It's almost like at this point there's only one thing. You want to somehow put this edge inside the tree, right? So you go ahead and add it to it. What happens when you add an edge to a tree? You create a cycle. So you can immediately say it forms a cycle. Adding this edge UV to the tree forms a cycle. Okay, and in this picture, notice that the cycle is clear. What's going on? It's some cycle. What can you say about this cycle? So this has weight alpha. What can you say about the cycle?
The other edge out of U has a weight larger than alpha.
There is at least one, not at least, there is exactly one other edge going out of U. And that edge has weight
Larger than alpha.
strictly bigger than alpha, because alpha is the minimum weight edge for U. So what do you do now? You remove this edge, put this edge, so let's call that beta, and we know for sure that alpha is less than. Okay? So we remove the beta, add the alpha, and then you get a better MSE, because you have added alpha. Okay. Notice that we didn't explicitly use the cut property or the cycle property. What we're using is something like the cycle property, but not quite. Okay? But this is the standard exchange argument for adding an edge, trying to argue that it belongs to the tree. All right, any questions? Yes?
This is an example, so is that?
This is not an example. So, okay, good. So the question is this an example? So no. So how would you write this out without drawing a picture? Yeah, a picture is perfectly fine. If you draw this picture, that's good. So how would you write this out without drawing a picture? You would say the following. You would say, okay, suppose UV not belongs to T. Adding UV to T forms a cycle C. C has one other edge UX, where X is now equal to V. Okay? Weight of UV is strictly less than UX. Removing UX, we use the new spanning tree. So how do I prove, here I'm implicitly, there is an implicit proof. How do I prove that if I add UV and remove this, I still have a tree? A spanning tree. How do I prove this?
By the cycle.
Pardon?
By the cycle.
Sort of, not the property, because the property is about the weight not included. But how do I prove that if I add this and remove this, everything stays connected?
Since there's a cycle, there's always another process.
So, and the way to argue things like this is, look, anything before that did not use this edge is still there, right? All the paths that did not use this edge are still there. Any path that uses this, that used this edge before, can instead now use this path. Okay, so that's the way to prove it. We don't have to prove it. We will often just say this like this. So if you're removing UV, you use spanning tree. Let's call this spanning tree T prime. Weight of T prime is less than weight of T. Again, why is that? Because the weight of T prime is the weight of T plus the weight of the edge UV minus the weight of the edge UX. And you're adding some smaller number, subtracting a larger number, which is a contradiction. So our assumption that we made early on is false, so UV has to belong to it. Okay? Yes?
So we remove that because the edge coming out of this
Yeah.
reason.
Yes.
And we directly could not use the cycle property because we're talking about the minimum weightage of the coming out of U rather than the entire graph.
Good, that's a good question. Actually, we can use the, so the question was, why did we remove beta? Could we have removed some other edge? And the answer is yes. Meaning the cycle property says that when you add this edge here, it forms a cycle. Ideally, which edge should you remove from the cycle? The maximum weight edge. So you could say, I'm going to remove the maximum weight edge. But then you'll have to argue that that maximum weight edge is not alpha itself. Right? What's the point? You just added alpha, and you're going to say that I'm going to remove the maximum weight edge, and you go ahead and remove alpha again, then you're done. So you'll have to show that there is some other edge that is bigger than alpha. Something else. Okay? The only information that we have about that is that alpha is the minimum weight edge associated with U. So the only other edge we know in this cycle that is bigger than alpha is this one. We have no idea that this edge is bigger than alpha. We have no idea that this edge is bigger than alpha. It could be. If it is, then of course we will remove it and we are done. But we have the only thing we know for sure is that this edge is bigger than alpha.
Can the max and the minimum be same? Because here it is distinct.
Excellent. So the max and minimum cannot be the same. So in this case, that's why beta we know is strictly bigger than alpha. That's the reason we know that beta is strictly bigger than alpha. Yes?
Just want to clarify, so the example on the left you gave disproves the claim you made up there, but the one on the right seems to support it. So are we saying that the claim is true or false?
No. This was an attempt at trying to show that the statement is false, but it's an attempt that fails. Because what was the attempt? The attempt was that, look, the attempt was something like this, so this is alpha. It forms a cycle. It's possible that alpha is the maximum weight edge in the cycle. That was the claim. But the point is, it's impossible for alpha to be the maximum weight edge of the cycle, while alpha being the minimum weight edge for U. Okay, so the argument went like this. Okay, UV may form a cycle in G, and UV may be maximum weight edge of the cycle. Okay, the argument was UV may form a cycle in G, plausible, and UV may be the maximum weight edge of the cycle. And by cycle property, if that is the case, it should not be in the MST. Okay? Then by cycle property should not be in MST. Okay? That was the argument trying to argue that this statement is actually false, because our question was, is UV belonging to the tree or not? And the statement was, oh, it's possible that this statement is false. The only problem is, this cannot be true. It's impossible for UV to be a maximum weight edge of any cycle, because UV is the least weight edge for U. Any cycle containing UV should have another edge for U. And if this is the least weight edge, how can that be this has to be smaller than this. So it cannot be the maximum weight edge of the cycle.
The claim you're making is that UV has to be the minimum weight edge. I was just wondering, because if you had an X, let's say.
No, UV is given to be the minimum weight edge already. UV is the minimum weight edge already. That's given to us. So UV cannot simultaneously be a minimum weight edge for U and a maximum weight edge for a cycle. That's the thing. Okay. All right. So let's go back to Kruskal and try to look at a really interesting data structure that allows us to implement this algorithm efficiently. Okay. So let's okay, so we observe that this can be done in order n log n, sorting of m is the number of edges and n cannot be any more than n squared, so that's a bound. And then here we are repeatedly checking whether E forms, whenever we add a new edge, we are checking whether it forms a cycle or not. Okay? And one way to do it, we observed, was we have written an algorithm or something like that to find cycles. So we can do a BFS, depth first search, BFS, whatever from an edge, and try to see if it forms a cycle or not. But that's too expensive. We'll try to do it we'll try to implement this in a smarter manner. Okay? So the way we will implement this is, remember, what are we doing in Kruskal's algorithm? We are trying to maintain different connected pieces. Okay? So at any point of time in Kruskal's algorithm, there might be a piece that we might have selected already. Okay, this is the three edges that we have already picked. Here, this edge might have been already picked. These three edges might have been picked. This edge might have been picked. And some of the other vertices, nothing might have been picked. This might be the situation in the middle of Kruskal's algorithm. Okay, what do we do repeatedly? We look at an edge, we check to see adding that edge creates a cycle. We are looking at all the edges in increasing order of their weight. If it forms a cycle, then we don't, we throw it away. If it doesn't form a cycle, we'll go ahead and add. Okay, so now let's say A, B, C, D, E, F, G, H, J, L, M, okay, so let's say these are some of the vertices there. Now if I give you an edge Hj, what will you say? Can I add this?
No.
No. How did you decide?
Vector cycle.
So how do you tell whether something makes a cycle? Do you have to look at the edges that you have already added to determine whether it makes a cycle? Okay. Let's say I didn't draw the edges inside, but I showed you the vertices in each component. Can you tell? So I didn't show you this picture, I showed you these are all somehow connected. And then I showed you the edge HI. Should you add it? If I let's say I showed a black box here. H I L
J.
J. I showed you this picture. I tell you that I picked up edges that connects them. That's why they are in the same component. Now I tell you, HJ, can I add it?
No.
No. Okay. Why is that? Because they are already part of the same component. So if I add an edge, I'll form a cycle. So the actual structure of the tree that we have built in is not that important. What's more important is which vertices we have connected, which vertices we have not connected. Okay? Good. So here is the problem that this leads to. Okay? And by the way, let's maybe ask you one other thing. So let's say this is the picture that it looks like. I'm removing all these edges, but this is the situation right now. HJ, you said no. Good. PN, edge between P and N, there is a P sitting there, and N?
Yes.
Yes. Okay, why did you decide that? They were in two different clouds. What do you do after that?
You merge the clouds.
You merge the clouds. Okay? So you really want to just replace that by so from this view, of course we are storing all these edges. We are adding all these edges to our tree. So we are going to eventually return a tree, a whole tree with all the edges and so on. So that's not our worry. But from this picture, all we are trying to do is we are checking to see two vertices are in the same set, and we are sometimes trying to merge two sets. Okay? So let's say that's your job. Your job is to come up with a data structure which maintains these things. So it's like completely independent of graphs to some extent. It's just, I give you a collection of sets, these are all disjoint, and periodically I might ask you, are these two things in the same place? And you might say yes. Or you might say no. And periodically I will say, okay, go ahead and merge these two. That's all that's going on. Okay? So this is what is called disjoint set. How many elements are there totally in this set? From the point of view of Kruskal's algorithm? The number of vertices, right? N. So you have a universe of n elements. Initially, these elements are simply written down as separate sets. Okay? So let me write it as 1, 2, 3, and initially this is what you're given. And then I give you a few operations. What I would do is I would like you to check if I and J are in same set. Okay? And I would like you to periodically merge two sets. When I ask you to merge two sets, how do I identify those sets? In that situation, if I'm adding the edge Pn, then I would like you to merge the set belonging to P and the set belonging to N. I don't give you the sets, I just tell you, please merge the set belonging to P and the set belonging to N. So I could do this, or I could do union I and J. Okay? Union Ij means merge the sets that belong to you, that contain I and contain J. All right, so how do I go about doing this? So there are of course many data sets that you could use. You could use things like hash tables, which keep track of these sets. The one problem with using hash tables is keeping track of which set they belong to, because then you'll have to use a second hash table to figure out which set they belong to. So let's think of simpler data structures and see whether we can manage this. So one really simple way to do this is, let's suppose you keep track of a linked list for each set. Okay? You just keep a linked list for each set. And you keep it doubly linked in case you need to remove or add or things like that. So let's say your sets were 1, 5, 7, 2, 3, 11. Okay. Now, one problem we face immediately, and let's suppose in many situations we always have a handle, a pointer to every object. So if I want to find 9, I know 9 is here, so I have a pointer to the 9. But I need to be able to check whether two things are in the same set. Okay, how do I do that? Well, one way to do it is to, you give me two things, I just visit everybody in that set. Okay, I just check everybody in that set. That seems too wasteful. All you need is both of these should share something in common, right? So one very simple trick you could do is have everybody, let's say, point to the head of the list. So they all have a pointer saying what's the name of the list or something like that. They all have a field in their object field saying what's the name of the list. Okay? So what is the name of the list to which 5 belongs? 1. What's the name of the list to which 7 belongs? 1. Name of the list to which 11 belongs? That's 1. That's 2, and so on. Okay, so it's pretty straightforward definition of. So now if you want to check whether 5 and 3 belong to the same list, what do? You simply look at this pointer and see whether it belongs to the same list. Very easy, right? So this checking, this finding, how long will this take? Constant time, just one lookup. All right, so that's easy. What about merging? If I tell you that I want to merge these two, what do?
Change the pointer.
So what do at this point?
Add 2
Pick the shorter one and change the pointer to the longer set.
Okay, so one thing you want to do is put them in the same linked list. Now there is not necessity, you could try to put them as a tree, but that's more complicated to think about. So let's put them in the same linked list. So in order to put them in the same linked list, all you need to do is put one behind the other. Doesn't matter which one you put behind the other in some sense. But crucially, you'll have to change these pointers. Okay, and that will require work. Connecting one app behind the other is trivial. But assuming you have a handle on the end as well, but it's fairly straightforward. But changing these pointers is challenging because it requires work. But the point, as was mentioned, is what you should try to do is change only the pointers for the smaller list. So at least you do less work. Okay, so let's see what you will do. So when you need to do the union of these two lists, you leave 2 as it is. Okay, 1 comes here, and you move all these pointers to point to 2. Yes.
Can you just have a pointer from 1 to 2?
Good. So you could. So the question was, can we have a pointer from 1 to 2? So that then when you go from 7 to 1, then you go one more hop to go to 2. So the answer is yes, you can. The unfortunate thing is now you don't have a guarantee that IN1, the check that you're doing when IN1 are on the same set, remains constant. Initially, of course, it remains constant. You're just doing one more lookup. But then as things build up, then you might be doing one more lookup, and then you might be doing one more lookup. It turns out that there is a really beautiful study of data structures like this, where that is a good idea. Because what you can do later on is, if you're going to 1 and then going to 2, at that time, why don't you just go directly to 2? Change the pointer to 2. And there are these lots of interesting things you could do, much more complicated to analyze, which we don't have. Yes?
So I'm a little confused about why the lookup.
Yeah.
Are we like, don't you just iterate through that?
Good. So the question is, why is the lookup with, to do an each kind of check constant time? Because don't you have to iterate through the linked list? It really depends upon how this check is invoked. When I say that check ij, means I'm actually giving you the object I and the object j. So I'm giving you a handle on these two objects. So you have the locations already. And then you want to check whether they are the same. Now if you did not have these pointers, then you will have to go through the linked list to figure out where they are. But if you have these pointers, all you do is look up their head and then check whether they are the same.
The pointer doesn't start at the beginning. Like, you have a pointer pretty much for
You have a handle for everybody.
Okay.
Yes. Yes.
Why can't we just use something like unify? We could use a array instead of this unify.
Okay. Let me. I'll answer that in a minute. So let me finish this. There's one comment I want to make, and then we'll go over the array possibility. So what does this do for you? So let's try to understand what's going on. So the main purpose, we are studying this data structure. One of the main purposes is its use here. If E, so how does this translate to what we want? When I'm asking this question about whether E finds a cycle or not, how do you find out? So let's say E is the vertex edge UV. So what I check is if find the head for U. If it's not the same as the head for V, that means they are in two different sets, you can go ahead and merge them. Then what do? You add this edge to your thing, to your tree, and you do a union UV. Okay? So notice that this is all that we are doing. Find the head for U, find the head for V. If they are not the same, if they are the same, this edge forms a cycle, throw it away. If they are not the same, then we will take a union of the two sets. Okay, so now this is a completely specified algorithm, right? Now, how many times are we going to do find U and find V? How many times are we going to call find?
And
Well, think about it. How many times are we calling this?
overall,
Yeah, we are going to find U at most n times, but how many times are we going to enter this for loop? The number of edges, m, and for each edge we are calling two finds. So the number of times we are calling finds is 2m at most. How many times are we going to call the union? Every time we call a union, what happens? Two things merge. Right? Two things merge. So the maximum number of times you're going to call union is n minus 1 times. What's the running time of find? Is that constant? So this is order m. What's the running time of the union? How large can a union, how much time can a union take? I have two linked lists. I'm changing all the pointers from one linked list to the other. So what's the worst case running time for union? N. And actually n over 2. Right? Because we are moving only the pointers for the smaller one. But it could be as much as n over 2. So the best bound, I can say that for each union is order n, and that will give me an order n squared. Okay? And I have to add all of that to m log n. Right? So if I had to write all of this, what do I get? I get m log n, n, and n squared. Right? What happens in terms of asymptotic notation? Notice that m is dominated by m log n. So I can ignore this. What about between these two? Well, if the graph has a lot of edges, which could be as many as n squared, then this dominates that. But if a graph has very few edges, then this could dominate this, right? Because the graph could have just a linear number of edges. In fact, most real world graphs do not have n square edges. That's way too many edges. Okay? So then this running time, you would simply read it like this. This is what we would say. However, this is a weaker analysis. It turns out this is only n log n. And we'll go over that just now. And here is a different kind of argument than we have seen until now. It is true that a union could take as much as n over 2 times. And there are n unions, so the total time you might think is no more than n squared. That's true. However, let's try to understand what's going on in a union. Okay? What is the work that we are doing in the unions? There's only one kind of work that we are doing in terms of literally the activity that we are doing. When we are doing two unions, what is the work that we are doing? Changing pointers. So rather than trying to look at how many unions, how many pointers, let's just take a look at these pointers that we are changing overall. What happens when, so in this case, how many pointers we are changing when we are merging these two? 3. So let's focus our attention on one vertex. I'm going to ask, how many times do I change its pointer? In this example, once. Okay? But overall, how many times am I changing? Is the question. If I could be changing a pointer for a particular element n times, then I will get back n squared. But perhaps I'm changing it for fewer times. Let's see what's going on. Every time I change the head of a vertex, what happens to the size of its set? At least doubles. Every time I make a change for its head, it at least doubles. So how many times could I possibly be changing its head? Log n times. Okay? So number of times, so each time head of a pointer, head pointer. This is what I'm referring to as head. Each time head pointer for any element, let me fix element I, is changed. Its set doubles, at least doubles. Since the set finally is only of size n, the number of times you can double is at most log n. Therefore, the number of times the head pointer can be changed. For I is order log n. Is actually less than equal to log n. So n minus 1 unions, and there are only n elements, so n minus 1 unions only takes n log n time. So the running time now is order m log n plus n log n plus m. But that's nothing but yes.
Couldn't you do an arithmetic sequence because you're doing half plus quarters plus eighths?
You could. The only problem is it's difficult to. It's something like that is what's going on, but what is going on is there are a number of different sets. So you might be taking a union of two things that are too small at this point. Then you might be taking a union of two things that are much bigger, and putting that as a sequence is more challenging. Here we are just taking a different view of how things are being added.
But if you're always adding a smaller, why does that not benefit you if you're having different sized items?
It is true, yes. So you could try to argue that the worst case scenario is that you are taking the sort of, you take two of things of size 1, 1, 1, then you make them 2, then you make 2, 2, 2, 4. You could argue that.
That's the worst case.
Yes, you could argue, but to argue that it's the worst case, you'll have to say something. So why is that the worst case? That seems like the worst case, but why it is? This is a more direct argument. Look, whenever you make a change to a head pointer for an I, it goes from a set of size, whatever it was, to a set of size that has grown at least double. And it can only happen in There was one other question. Let me answer the question about the array first, and then I will take other questions. So, one question was, what if you maintain things in an array? So, there are different ways to do that. One is, you might have a single array where you list for everybody what set it is in. Or you might have multiple arrays that list the different sets. Okay? So let's say you have a single array that lists for everybody what set it is in. So initially they're all in their own sets. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say you merge 3 and 5. Then you want to change that to so you're merging 3 and 5, so you change both of them to say 3. Okay. In order to then the find, how long will find take? Find will be very easy. It just takes constant time. But merging is so how do you merge is the question. Right, so how do I, so if I tell you I want to merge I and J, how do you merge that? Well, so you go, how do you find out all the things that belong to the set for I? Well, so notice that, are we keeping, so you can, how do you tell all the things that have I, so let's say, how do you tell in an array all the indices that have 3 in it? You'll have to store other pointers, otherwise you'll have to just go through the whole array. Okay, so remember in general, You have this array. The so all of these have 3 as their head. How do I find all of these elements out? So I have to keep some kind of pointer, but then that's the same thing as the linked list. Okay. I think just using an array will take you quadratic time. Okay, we can go with that. There was one question. Yes.
Why is the final complexity m log n? Because again we can have more number of vertices or more number of edges.
So why did we ignore n in favor of m? Yep.
Because the max possibility for n log is way more than the max for n log n.
Okay, m is more than, certainly m can be quadratic in n. But notice that the graph is connected, so m is at least n minus 1. Okay, so m is at least n roughly, and it could be much more. So you can always ignore n. Yeah.
Why don't we have a hash map where the values, like if it's a good decision to have a string of whatever is there, and where the key is that, and the values will be the linked list. So it'll be easy to merge, and for lookups also to see.
Two
that
things
is there.
belong. You can do that. Yeah. You can. Yeah.
So earlier you said that we all just want to merge the smaller of the linked list with the larger of the linked list.
Yes.
So in the statement you have there, why don't we say at most doubles rather than at least? Because
No, notice that. So look at the one, so you're taking 2 lists. So the question is, why do we have this at least double? Okay. So look at this is being merged with this, right? Which elements did we change the head for? 1, 5, and 7. Look at their perspective. What is their community population right now? 3. What is their community population after the merge?
that's referring to this.
Yes, they're referring to. So we are only referring to those things which we changed, because that's the only work we did. We didn't even touch any one of them, and that's all we can. Okay, I think we'll move on, because we are going to move on to the next segment. Called dynamic programming. So, dynamic programming is the term, maybe don't worry about the term programming there, but basically it's a technique for solving optimization problems. Very much like the kinds we have been looking at. Okay, we looked at interval scheduling. We will be looking at a more general version of interval scheduling called weighted interval scheduling. Actually, I may not do that today. I will do this part next class. I'll pick a different problem today called longest common subsequence. So it's a technique for solving optimization problems. It has strong connections with 2 techniques we have already seen. One is divide and conquer. And the other is greedy algorithms. Okay, but arguably it is more sophisticated in both of these techniques. The similarity to greedy algorithms is that in a greedy algorithm, what do we try to do? We try to identify some choice we can make right now that we are sure will eventually be in the optimal solution. That's what the greedy algorithm is, okay? Notice that something I want to emphasize about greedy algorithms is that, and we will go over some more examples later on, that a greedy algorithm, there are many different greedy choices you can make at any point in a given. So there are multiple greedy algorithms possible. Just because an algorithm is greedy does not mean it should work correctly. There are multiple choices you can make. And so it's not clear what that greedy refers to. Is there only one greedy choice for the given problem? No, there could be many different greedy choices. When a greedy choice works, it should work for the final objective. Okay, that's the main, ultimately you're solving the final objective, right? So the greedy algorithm refers to the fact that you can make a certain choice right now and commit yourself to that, and you're sure that that's going to be in the final outcome. Okay? Good. So it is being able, so it is identifying some piece of the optimum. Okay, I'm just informing you. It's identifying some piece of the optimum that I know for sure exists. I take it, then my remaining problem is a smaller problem, and then I repeat. Include it. Reduce the problem. Okay? All right. So, dynamic programming also tries to analyze the structure of the optimum. Okay? Before you even come up with an algorithm, you try to understand the structure of the optimum. So you somehow, while you're not able to determine a specific thing that you know for sure, you're able to identify pieces of it, saying that, oh, perhaps it looks like this, perhaps it looks like this, perhaps it looks like this. So what it does, a dynamic program structured okay, and then splits breaks the problem down into smaller problems, just like divide and conquer does. Except, rather than sort of cleanly dividing the problem into disjoint problems, like divide and conquer does, it actually splits the problem down into perhaps many, many overlapping subproblems. And then it sort of repeats. And the way we solve dynamic programs is by giving a recurrence. Okay. This recurrence, the meaning of the word recurrence here is exactly in the same sense as the recurrence that we were talking about for running times of algorithms and T sub n. But the way we will use it is very different. Okay? But the idea is the same. I describe a recurrence that shows how to solve bigger things by solving smaller things. Okay? One comment I would make is arguably students find this the most difficult part of this course. Okay, so but there is a very clear method to this. So once you get the hang of the method, the only way you're going to learn, you're not going to learn by listening to me, by listening to the videos. The only way you're going to learn is by working through problems. The more you work through, and the book has many, many, many examples, just the more exercises you do, the better you will get it. Okay. There is a very specific way in which we'll do it. And finally, if you think about it, when we solve a DP, the only thing we need to figure out is how to solve the recurrence. And the recurrence is literally 3 lines or 4 lines in most cases. So you have to figure out those 4 lines. But the way you do it, you have to go over it many times. Okay, so let's start with an example. We'll do a lot of examples, and dynamic programs are very powerful, and they are still heavily used in research. There are many applications in bioinformatics and networking and data science that you can apply this to solve interesting optimization problems. So let's start with this problem called the longest common subsequence. Okay. So there are many problems dealing with strings when you're trying to compare 2 strings and trying to arrive at some structure or commonality between strings. And one variety of problems, for example, looks at comparing genomes. You might have a long, or comparing 2 strings of DNA and trying to see whether they look very similar to each other. And there are lots of problems you can formulate, but one very nice problem that's of interest is if I give you 2 sequences, so let's say sequence X and sequence Y. Okay, and this sequence X is some number of characters, and then I give you sequence Y, another number of characters, and I ask you to find the longest common subsequence. Okay, what do we mean by subsequence? And there could be a difference of different definitions of it, but for the problem it's very clear. We say that Z is a subsequence of some given sequence X if Z can be obtained from X by removing some elements, just deleting some elements of X. By just deleting zero or more characters in X. Okay? Alright, so for example, G, C, T, C is the subsequence of X. Okay, the order matters. It doesn't matter that they are contiguous. That's all that matters. Okay? So is the definition of a subsequence clear? Okay? And what is the question we are interested in? Find me a subsequence Z, that is, find me a sequence Z that is both a subsequence of X and a subsequence of Y, but it is the largest such possible. Okay? So it captures sort of a structure between the two. And then if it turns out that there is a very long subsequence, then you might say that, oh, these two are very closely related. You only need to do a small number of changes to make them look similar. And so that will show you. So let's try to understand this a little bit better. So in this example, what do you think is the longest common subsequence? So
CG, AITA.
CG,
AITA.
Okay. So is the definition of the problem clear? Okay. Of course, there are many subsequences possible, and there could be many longest common subsequences as well. But you need to find one longest common subsequence. Okay, so that's the problem. So how do we go about addressing that? So let me just, before we do that, let's try to understand, let's set the problem a little bit more. You're given a sequence x1 through m, and you're given another sequence y1 through m. How many subsequences does x have? 2 raised to m, because for every character you can decide whether you want to delete it or not. So you have two choices. So you have 2 raised to m subsequences of x. How many subsequences of y do you have? 2 raised to m. So if you really wanted to try all possible subsequences, that's a non-starter. There are just way too many. And in fact, in biological applications, m could be millions and billions, right? So, okay, so that's not non-starter. So we should do something more clever. So you could try a greedy algorithm. Okay, so let's try that. So you could compare the first 2 characters. So in this example, you could start with the first 2 characters. They don't compare. So what do you do at this point? So certainly you cannot include both of them in your solution, right? So what do you do at this point?
Increment one, keep the other.
Do we increment both?
No, just one.
Then which one do you increment? Well, in this example, it seems like we should increment this because these 2 match, but in general, what do we do?
You increment one and check, you increment the other and check.
Okay, so let's say you increment this one and check. Then what happens?
It's not.
It's not. If that fails, what do you do?
You switch the pair to C and C.
Then you compare these 2. Is that what you said?
Yeah.
What if they also did not work out? Then what do you do? Okay, so the problem is at this point, it's not clear what greedy choice we can make. One thing we are sure, or maybe sure, maybe not sure, I don't know. But let's say A was not there. Let's say C and C matched. Then can you be sure that I should go ahead and match C and C?
Yeah.
Yes.
So there is something interesting here. So let's try to see whether we can prove it. Suppose x1 and y1 match, okay, is it the case that is x1 which is the same as y1 part of longest common subsequence? Suppose the first two characters completely match. Is it the case that it is part of a longest common subsequence? Okay, so this is what is called, sometimes referred to as an optimal substructure property that we need for greedy to work. Okay, but it turns out this is not as sufficient, because if it is not, what do we do? And that's where we were struggling. Okay, but let's try to see if this is true. So this is, we'll try to prove it. Okay, suppose now so here is your x, here is your y. These two are the same characters, alpha. We are trying to claim that this is indeed part of the longest common sequence. Suppose it's not. Okay, it's not. Let z be the longest of x and y. So what can you say about z1? It's not equal to alpha. Because if it was equal to alpha, then we are already. So it's not equal to alpha. So if it's not equal to alpha, that means it has to be equal to beta, which has to be lying on this side, somewhere here, and somewhere here. So what can you do? You can just add alpha ahead of that and find a new longest common sequence there. It's almost like a trivial algebra. Z1 is not equal to alpha, implies can add on alpha in front of Z. Okay? Okay, so but the question is, what do we do when it's not the same? So, and this is the struggle that we were having is, should I move this one to the right or move this one? And the idea is, yes.
We check for the first matching pair.
Aha.
We move either one.
Okay, so we could keep going until we find the first matching pair, but one question we struggle with there is, do I keep the other one fixed? And if I keep looking for the first matching pair on the right to match this, maybe I will never reach it, or the other way, and then I'm stuck. Okay, so the idea of what we will do is, we will say, all right, I do not know which direction to go, so I'm actually going to try both. I'm going to move this to the right and then try for this. I'm going to move this to the right and try for this, and pick the best. But if you just repeat this naively, you get an exponential blow. You get fact 2, then another 2, then another 2. So dynamic programming is about doing it in a smart way so that we don't repeat any of these. So we'll stop at this point, we'll complete this.